Hello everybody, this is Dr. Schoffes here, starting out with the first chapter 14 slides. Two main areas are discussed, and that is IR spectroscopy, infrared spectroscopy, and we do use a lot of abbreviations, and then we also have mass spectrometry, also typically referred to as MS. Okay. On the next slide, I have an overview for you. So I've broken this down into three parts. We're going to do the first part of IR spectroscopy now, followed by mass spectrometry, two very different methods for analyzing organic molecules. And then also this one here, hydrogen deficiency index, is an important tool for analyzing substances and confirming that you have a particular compound. Hydrogen deficiency index is the term that is being used in this textbook, also abbreviated as HDI. And in other books, it's also referred to as degree of unsaturation. Here I have a few keywords for you summarized for infrared spectroscopy. So you need to understand the correlation between the energy. Energy can be measured as wavelength and frequency, and specific bonds and functional groups. So this is really about functional group identification. I often also abbreviate functional groups as FG. So it's really important that you understand the connectivity of a functional group, that you can understand what type of bonds are present. For example, in an alcohol, which we can typically abbreviate as R, where we have a rest group, we have a carbon-oxygen bond and an oxygen-hydrogen bond. And that is the sequence. And then we need to look for evidence for certain bonds to see them in the spectrum. You need to understand what a wave number is. Sometimes we see certain bonds very well. We refer to them as IR active. Typically they're very polar, but they're also IR inactive bonds. I'm going to discuss the difference for this, and it's also part of the special handout I prepared that you can find and work with. We also are talking about molecular vibrations. Molecules are not just rigid, they actually vibrate all the time. The different terms, stretching, bending, scissoring. The dipole in a structure clearly determines how well the response will be in an IR spectrum. We need to be very careful and pay close attention to the diagnostic region. We look at that region first, and then we can look for secondary evidence in the fingerprint region. So you need to understand this. And then key stretching frequencies are also often referred to as wave numbers. All right, so here's some general introduction. Again, we're looking at the interaction between matter and light. And light, a more sophisticated term, is electromagnetic radiation. We can think of light as waves and packets of waves. Light travels in the form of photons. It strikes the substance, and then we look for the response, whether some of these bonds are vibrating or giving a specific, are vibrating or not in a particular region. Light waves can be described with wavelength, and we use the symbol lambda, and frequency, which is nu. Let me try this again, nu. And then we have an inverse proportional relationship between wavelength and energy, and a directly proportional correlation here. On the next slide, you see the electromagnetic spectrum. It goes all the way from gamma rays, like from radioactive material, to X-rays that you see on the left-hand side. Those are high energy waves, all the way to the less energy waves and less threatening energy waves, because not all waves are good, such as microwave, radio waves. And then here also a glimpse. This is what we can see with our eye. It goes all the way from purple to then red, and then when we talk about infrared, this is an area we cannot see, but this is how what this technology is based on, infrared spectroscopy. On this slide, okay, matter can have particle-like properties as well as wave-like properties. Usually we strike the molecule with light, it causes a vibration, and then depending on the types of bonds, we absorb different types of IR energies and we see a response. So again, you need to understand your functional groups. So matter on the molecular scale exhibits quantum behavior. This gets a little bit more abstract. Again, there are certain movements that are possible. And here are some images to show you we can have stretching and scissoring and twisting. So all sorts of different terms. When we're less concerned with those aspects and look more at the practical applications of IR spectroscopy. So make sure you understand all your bonding patterns in the functional groups. Here are some other areas where IR spectroscopy can be applied. For example, if you use particular goggles, you can see where, let's say, energy leaks out of your house. So often that is around doors and windows. We can also use the technology to actually look at potentially cancerous tissue. Here we have a comparison of two types of bonds. So we are comparing a CH bond, hydrogen is very electropositive, versus a CO bond. And here oxygen is very electronegative, it's very electronegative. And that has an influence on the vibrations, because we said we have certain spacing out of energy levels. So we have a larger gap here and a smaller gap here. What does it mean in practical terms? So IR spectroscopy, here are some things that are especially important if you're doing the lab. So we do have spectrophotometers. That is what these are called, spectrophotometer. It shines a light on the sample in the IR region. A frequency is absorbed. We can then figure out the types of bonds and therefore the functional groups that are present. Most commonly, in order to deposit or to prepare a sample, there are different ways. We can actually make a solution. Let me see how easy it is for me to write on here. So we can have a solution. But we can also prepare solid samples, and we either use salt plates with sodium chloride or KBr. Last but not least, again, understand the connectivity, the bonding patterns, and electron placement in all functional groups. So that is really, really important. And so I'm going to put here an exclamation point. So here in the second segment, we look at the absorption spectrum. We can have transmittance or absorbance, same difference. There are three important characteristics. When we are looking at peaks or absorption bands, the different terms, sometimes we say a signal. We are paying attention to three important characteristics: the wave number, which is correlated with frequency, the intensity, and the shape. So, for example, here I see something that's a little bit broader, and here I have some sharper peaks, but I also need to pay attention to the wave number and the region where this is. And there are some very important trends that we can outline. All right, so here's another illustration. Again, wave number, intensity, and shape. I'm already going to tell you that the first thing you need to do when you're analyzing IR spectroscopy is actually to draw two vertical lines, because depending on whether, so here are my two vertical lines. One is at 3000 and one is at 1500. Everything above 1500 is the diagnostic area. Sorry, I have a little bit. So this is going to be diagnostic area. I'm not going to write the whole word. And it's coming up later again. But these are the two lines I want you to draw first when we're analyzing these spectra. Okay, a little bit of theory. Here's a complicated equation. Don't worry, you will not have to do any calculations. But we have to pay attention to bond strength and then also the mass of the two atoms involved in a bond. And we see these two components reflected again in that equation. All we need to understand is that they play an important role. So how strong the bond is, and then what the mass is of the atoms that are involved. And then here, another very important aspect, I'm going to trying to put another exclamation, correlation. We have bond means higher stretching frequency, larger mass difference, also higher stretching frequency. Very important correlation to keep in mind. On this slide here, we now actually see a couple of examples. Here we are comparing, under the first part, we're with carbon-deuterium bond. Deuterium is an isotope of hydrogen, it's heavier. If we even more mass, and then here we have even more mass, and you see that the numbers go from 3,000 to 700. So we have a decreasing trend when the mass gets bigger, as we're comparing each carbon bond here. And then bond order has to do with, well, how many bonds do we have? Do we have a single, double, or triple bond? And guess what? The trend is we start in the fingerprint region below 1500, a carbon-nitrogen single bond. As we go and increase the bond order, go to a double bond, the number increases to 1600. As we go to a triple bond, it increases to 2200. Okay. So here's one very helpful tool in your textbook. So we're basically now here comparing single bonds, double bonds, and triple bonds, and see how they are all between same atoms. So we have carbon-carbon, carbon-nitrogen, carbon-oxygen. Here it's carbon-carbon double, carbon-nitrogen double, carbon-oxygen double. And then we can have triple bonds between carbons, and then here also something that would be in a nitrile functional group. And all the way to the left, see how it's above 2700, we have all the bonds to hydrogen. Okay, so that would be your carbon-hydrogen bond. And I also have this in the handout. And then you would have your nitrogen-hydrogen bond. So we have N. Yeah, my writing pad is not cooperating very nicely. And then you can fill in the last one, which is OH. And you see also something similar I marked up in the special handout I prepared for you for the IR chapter. So this is an N. Here's the nitrogen. Okay. On the next slide, again, this is just a different way of representing what's happening. We have a lot of single bonds on the right-hand side, which is called the fingerprint region. And that's why I wanted to draw two lines, because whatever is under 1500 is going to be more secondary. We look first and foremost at the diagnostic area, which means anything that is larger than 1500, okay? And then within that, you see we have double bonds, triple bonds, and then bonds to hydrogen. Okay, so here you have it written out again. Very important distinction for us. So if you were to analyze the diagnostic and fingerprint regions, it sometimes is difficult to tell the difference between two compounds. There's some drawbacks in IR spectroscopy, especially if we were to look at two alcohols, right? So if we have two butanol and two propanol. So the way you go about it, and this is something you can pause the video and you can think about, what does the structure look like? How many bonds do I have? We have a carbon-carbon bonds, carbon-hydrogen bonds, carbon-oxygen bond, and also an oxygen-hydrogen bond. And here you have two examples. In the beginning, you are given the structure to correlate, basically, what you need to understand, because both molecules have the same types of bonds, you know. It's just one less carbon. They're rather indistinguishable. So IR spectroscopy is no good for telling us how long a chain is. We really can only break it down to very specific bonds. Carbon-carbon, carbon-hydrogen, in this case carbon-oxygen, and oxygen-hydrogen. So here I tell you again, draw two vertical lines at 1500 and at 3000. Focus on everything that is above 1500. So if we were to do this here, right, so we can draw in our lines, especially at 1500, and we can do this again on the other side. These are very small, but you also have pictures in the textbook. When we're looking at this, we see that really these peaks are very important, and these are secondary. We can make assignments, but this is the diagnostic area. This is what we have to look at first and foremost, and then here too. And then you can see that I already know that when I draw in the other lines, so if I go to my 3000 line, so I'm already telling you how to interpret the spectrum. So let's do this on the other side as well. I now need to first look at the 3000 line. And I see here some stretches. And this is actually responsible for the carbon-hydrogen stretches that are in the structure. And this is very important because if it's below 3000, it tells me that the carbon is actually sp3 hybridized. And that's a very important distinction. And I see something similar here. So this is for your carbon-hydrogen, so you can make a note of that as you're entering into your Cornell note-taking modules. And then we also have a very broad one here, and these are actually very easily characterized, and these are typically OH bonds. So remember, all the bonds to hydrogen are high or to the left of the IR spectrum. So here we have the OH. Okay, on the next slide, here's the differentiation, okay? So it's really important that you associate the stretching frequencies for CH bonds. These CH bonds, it depends on what the hybridization is. So that's why I started us out with reviewing a lot of old concepts and theories from Orgo 1, because we're going to have to apply them over and over again. Hybridization. So this is an alkane or an alkyl carbon hydrogen. This is going to be below 3000. But if something is higher, well, guess what? We have to consider sp2, right? So that's one double bond at least. Now it's going up. And then if we have a triple bond with sp hybridization, it's going up even further, okay? So the higher the S character of the carbon, the stronger the CH bond, and so the higher the stretching frequency. So in an S and a P, the S character is 50%. Here it is 33%. Here it is 25%, right? So that's how this phrase comes into play. And then here are some examples again to look at. So closely analyze it. You may want to, stop the video or pause the video, and then analyze clearly. Again, that's why I had you draw these lines at 3000. So this is zoomed in, a little bit more visible, and you can see if it's below 3000, that's sp3. If if it is above, slightly above, around 3050 to maybe 3100, we now have to have at least one double bond here. That's where that carbon-hydrogen bond is going to show up. And this has to be a bond to another carbon. And if we go even further, this is the strongest bond. Now, see, we're actually past 3200. And then something else that's a little bit of a drawback is it's possible that you might have a double bond or a triple bond in your structure, but that it will not show. And this has to do with symmetry. Remember how we needed bond polarity? So if this is symmetric, then we will not see the sp2 hybridized carbon-hydrogen bond. The same is true for a symmetrical alkyne. And I also incorporated that with some additional information in the handout I posted. So look for the newly available notes version of that. We have color-coded and added a lot more information. Resonance, another reason why I wanted you guys to closely review resonance, which shows up in chapter 1, 2, chapter 6. And delocalization is going to be very important when we move forward and discuss conjugated systems in a few chapters, and of course also with aromatic systems. So if we have resonance and we can delocalize the electrons, it will actually now affect the wave number. Okay, so resonance is possible in this one. This one has resonance. Because we have a double, single, double bond, and so you should go ahead and draw the possible resonance structures. And remember how we use a double-headed arrow in order to indicate this very special equilibrium between resonance forms. And we can actually draw 3 structures for this, and we can only draw 1 structure for this. So the carbon-oxygen double bond will never, there will be no effect on or no communication with the rest of the structure. And see what happens. So if it's a regular ketone, it's at 1720. If it's a conjugated ketone, it moves to a smaller number because the double bond character here is actually closer to a single bond character. And remember how we went from the right to the left, from single, double to triple? So there is more single bond character in this structure here, in this carbonyl group, in this carbon-oxygen double bond. Okay, because you're going to have to average out the either 2 resonance hybrids here, and then there are 3 for this one. So, but here is the answer. So I hope you try to honestly figure out how to get there. Here are the possible resonance forms. We can first move these 2 electrons from the double bond up to the oxygen, creating a negative charge here, and you're taking electrons away from the carbon. So that's why you need to be really good with formal charges. While here, we can delocalize. Remember, oxygen is electronegative. It can grab on. It's getting a negative charge. Then we have a positive charge here. And now this is in conjugation, and we can draw another resonance hybrid by turning this into a single bond. Here you have it. And this single bond here now becomes a double bond. And this one just remains. Okay, but if you now look, here we have a 50-50 ratio of single bond, double bond character. Okay, and that gives us the stretching frequency of 1720. While here we have double, single, single. So we have more single bond character. And now we see a decrease, and the numbers move to the right, move to smaller wave numbers in your spectrum. We can also see this with other functional groups that we will discuss in the future. I don't necessarily want you to remember or memorize 1720 or 1740, but you need to understand the trend. So here are 2 more examples for, so we had just worked through this one here. We can see the same thing with an ester. Ester has a carbon-oxygen double bond and then an alkoxy group. And if we introduce conjugation here, and you have a double bond here, then you can again formulate more resonance structures. And we're seeing again a decrease here, in this case from 1740 to 1710. And remember, you have lots of conceptual checkpoint portions in your book for practicing, and practice is the key, and for you to write down things. But of course, you should always start out with first reading through the textbook, then looking at the videos, and then practice through all sorts of things. Orion is optional, so it's really up to you. Okay, intensity, fairly straightforward. This is considered a strong intensity. Transmittance goes sometimes all the way down, and here we have a weaker signal, right? So it doesn't go as far down. Here's something else. So remember how I started out the whole discussion about bond polarity? Well, you're going to get a stronger IR signal. And the two examples that are given here are a carbon-carbon double bond, and see how the vibrational mode is just much more flat, and then that translates to a weaker signal. And then here in the carbonyl group, more bond polarization, see how the vibration is very different in shape, and that translates to different outcomes in your spectrum. So we typically, the carbonyl groups are very easy to spot because they tend to go really all the way down. Here you have an example, versus a carbon-carbon double bond in an alkene. See, this is much smaller. And we also look for these in a different region. We also want to understand that some of them can have a narrow so we can have a narrow signal, while others can have a broad signal. And a broad signal is really it's very indicative of the hydroxyl group, an OH group, right? So you have an OH group and an alcohol or in a carboxylic acid. So we need to pair up all these bonds with the functional groups, and then we look for that in the spectrum. Here are two examples, and I've also incorporated a couple of spectra in your handout. When possible, OH likes to form hydrogen bonds. Yeah, so this is also an old concept you should remember from general chemistry and from Orgo 1. And we can actually associate free, so uncoordinated, unhydrogen bonded OH stretch, which shows up a little bit more sharp. But the OH, that is, and usually we have this as the overwhelming signal, OH participating hydrogen bond, that's going to be quite broad, right? And remember, it's to the left of 3000. And then here we have, when we're looking at a carboxylic acid, we can have hydrogen bonding here as well. And it's going to be so strong, it actually will start to partially drown out or overlap with, so this is sort of like the OH stretch, and it overlaps with this region here. So those are your CH stretches below 3000 for a saturated carbon, but this OH is very overwhelming. And of course, we also then see always above 1600, we see the double bonds, and this is a strong carbonyl group. So, and I filled out some information on your worksheet as well. So we're looking at different shapes as well. So we have primary and secondary means. And if we have NH stretches, remember on the left-hand side of your IR spectrum, that's where your carbon, your oxygen hydrogen bond is, your nitrogen hydrogen bond is. And here we see something really interesting. It's really very powerful. We can determine whether we're dealing with a primary amine or a secondary amine. This is a primary amine here on the left. It has only one rest group below here and two nitrogen hydrogen bonds. Okay. If we have a secondary amine, there's only one NH bond in here. So there are other rest groups here, and then we only see one spike for this, or one signal. And again, they're going to be over 3000. And if we have a tertiary amine, we have no signal because there are no nitrogen hydrogen bonds, so we won't see them. So when you're analyzing your IR spectrum, you know, I also wrote down some other things on your handout. You have tables summarizing. It's best if you understand the trends. We first, again, functional groups. This are going to be your signature stretches or key vibrations that show up in the spectrum. So diagnostic region, roughly 16 to 1800 or 16 to 1850. Check for double bonds: carbon-carbon double bonds, carbon-oxygen double bonds, carbon-nitrogen double bonds. Here, check for triple bonds. You only have two kinds: carbon-carbon triple bond, carbon-nitrogen triple bond. Unsymmetrical, remember that. And then we have the lighter bonds. They start actually at 2700 because we have the aldehyde group in there. More about that later. So you want to analyze the wave number, so where they are, the intensity, as well as the shape for each of those. So here you have some examples. So as you're analyzing the spectrum, so as you're looking at this region 2700 to 4000, you can then recognize different positions of what we would see. Again, I want to have you write this 3000 line, and then we focus on what's above. SP2, SP. Here is one example. So you're going to have primary, secondary amines. You're going to have hydroxyl groups from alcohols or carboxylic acids. So we often use IR spectroscopy to distinguish between two compounds. As we've learned in previous chapters, chemists often carry out reactions to convert one functional group into another. Here's an interesting example when you were studying alcohols in Orgo-1. This is the symbol for just saying we do some kind of oxidation procedure. You're now increasing the carbon-oxygen bonds from single to double. So we have an alcohol to a ketone. We would expect a significant change in the spectrum. And that is why this is really very helpful. So please look at the handout that I've posted on e-learning, but also remember that there is this website here. It's called Spectral Database for Organic Compounds, SDBS. You can look at many examples. Not all spectra are very instructional, but and there can be other more sophisticated aspects to interpreting compounds. But if you wanted to look up some simple alcohols or ketones, and the more you look at these spectra, the better you will get with interpreting the meaning of these spectra. I'm just going to quickly click through. This is in your handout as well, but so please know that in the handout you have an example for alkanes. You are given the structure and the name, so it's fairly easy. So analyze the bonds and work through it. The following are alkenes. Here's an example from alkenes. The next one is aromatics. So you should pause the video and then look at these in detail and see what you can analyze. Here's an alcohol. Remember, these are just really telltale signs that there's a hydroxyl group there. Followed by carboxylic acid, right? So here we see something similar. This is for butyric acid or butanoic acid. Aldehydes, we have two peaks in this area that are going to be for the carbon of the aldehyde functionality. So look at the handout there as well that I have posted on e-learning. And of course, look at many examples that are in the textbook. Here we have an amine. We can immediately tell it's a primary amine. It has two nitrogen-hydrogen bonds. Okay, so it's a very powerful way for interpreting structures. So as you're looking at this, you can of course then look at, as you're analyzing the reaction, which bonds will disappear, which bonds will appear as you're doing your spectral analysis and confirming what you need to know. And we're going to stop here before we go on to the next segment.